Hello everyone, welcome to Northern's Craft. Today we are going to have a steady flow energy equation for an open system. So, rate of heat interaction. It says rate of heat interaction is equal to rate of work interaction in control volume plus rate of kinetic energy in interaction plus rate of potential energy plus rate of internal energy. So, here rate of kinetic energy is equal to half mass interaction into rate of mass interaction into velocity at output square minus velocity at input square, and potential is equal to mass interaction, rate of mass interaction into acceleration due to gravity into height at output minus height at input, which is given by Z0 and Zi, and enthalpy, which is rate of enthalpy interaction, is given by rate of mass interaction into enthalpy at output minus enthalpy at input. So this is the general energy steady flow energy equation for the open system. So now we will talk about its different types, or for the different devices we can say that, or we can say its application. So let's first talk about nozzle. As we know, the way nozzle looks, this is the nozzle. It's the steady flow device, we know that, which increases the kinetic energy, and nozzle are used in jet propulsion as well, jet propulsion system, and at the inlet of impulse turbine. In this, we assume that subsonic flow speed is less than that of in sound. We assume that this is a subsonic flow, and nozzle is a converging duct, and so this is our control volume. Liquid flows from here and goes out from here. So as you can see, this area at output, this area at input, velocity at output will be C0, velocity at input will be Ci. So just by saying our general formula, rate of heat interaction will be equal to rate of work interaction at the control volume plus rate of kinetic energy plus rate of potential energy, change in potential energy, plus rate of enthalpy change. In this diagram we can clearly see that there is no control work interaction in the control volume. It means like there is no change in control volume work interaction, since for that there needs to be some change in like electrical energy, potential energy within the control volume, but steadily the liquid flows from here and comes out from here. In case of our general formula, in this case we have taken another example in which we know that in this general equation we solve it by showing a rotor inside the open system model, which help to determine the control work, rate of control work within the system. But in case of nozzle, there is no rate of control work within the system, so we consider this as 0. It becomes 0. So therefore, our formula for steady flow equation for the nozzle will become rate of heat interaction will become rate of change of kinetic energy plus rate of potential energy plus rate of enthalpy change interaction. This will be our steady flow equation for the nozzle. If we divide this equation by mass flow rate of mass flow, then our equation becomes, if we divide by this, then our equation becomes Q is equal to energy, heat transfer will be equal to change of kinetic energy plus potential energy plus enthalpy change. And by the way, we know that the unit of rate of heat transfer is in watt or kilowatt. We know that its unit is watt or kilowatt, you can say. But in this case, in the second case, our unit becomes joule per kg or kilojoule per kg. So this is the equation for the steady flow equation for the nozzle. Now we will talk for the insulated nozzle. In case of an insulated nozzle, the potential energy also becomes zero, since, and heat transfer also becomes zero, since the height of both Z0 and Zi will be same in this case. I will show you my drawing diagram. This is our nozzle, where liquid flows from here and it goes out from here in case of nozzle. But this is insulated case on both sides. In this case, the Z0 and Zi are equal, and we know that in insulated system there is no heat transfer. Therefore, our equation becomes rate of kinetic energy change plus rate of enthalpy change is equal to 0. This is the energy equation, steady flow energy equation for the insulated system of a horizontal nozzle, or by dividing the mass flow rate is given this formula. Now we come out to our next part, which is diffuser. Before knowing the steady flow energy equation of a diffuser, we must know what is diffuser. Diffuser is a steady flow device which increases the pressure, and it is used in centrifugal compressor. So I will show you the diagram of diffuser. As you can see, it's quite like opposite that of a diagram of a nozzle. In this case, liquid flows from here and goes out from here. Pressure is P0 at this place and Pi at this place, and area is A0 at this place, and pressure is Pi at this place and AI at this place. So in this case also, we can see there is no control volume work. So therefore, our heat transfer equation becomes rate of heat interactions is equal to rate of kinetic energy change plus rate of potential energy change plus rate of enthalpy interaction change. This will be the equation for the diffuser as well. And in case of isolated system in a diffuser, this is our diffuser. Again, when it is insulated, well insulated and placed in a horizontal direction like this, which goes like this, then our equation becomes delta kinetic energy change plus delta H change rate becomes 0. This point in above determines, it says like it's a rate, and when it's divided by the mass rate, the rate of mass interaction, it becomes K plus del H, which is equal to 0. Now we will talk about our next energy flow equation where we applied, which is turbine. we'll see how in turbine it's applied. We know that when some energy is got by the turbine, it will give the output as well, and it will give the work output as well. So inside of this there is a rotor. When the water flows from here, it helps to rotate this, and the water goes out from here, and the energy is generated from there, where this will be the positive work output. Pressure at output and pressure at input, and we know that pressure at input is greater than pressure at output. So as you know, turbine is a steady flow device which is used to produce power, and it is used in a gas turbine power plant and a various power plant like hydroelectric power plant. As you know, in the dam it's also used. For this system, the steady flow energy equation is rate of heat interaction is equal to rate of control volume work plus kinetic energy change rate plus potential energy change rate plus enthalpy change rate. Since in this case there is a control volume work inside it, that's why we applied over here as well, and we followed our general formula itself. And the unit of this, as I have said, unit of this is in watt or in kilowatt. And when we divide the above equation by the mass flow rate, it becomes Q is equal to omega CV plus delta KE plus delta PE plus delta H, such that its unit is joule per kg or kilojoule per kg. Now we will come to compressor. As nozzle is quite opposite that of a diffuser, similarly compressor is quite opposite that of a turbine. So if you see, there is a rotor inside, and power is given by us to the rotor, and power input is from this side and output from this side. Output is from this side. Compressor is a steady flow device which is used to increase the pressure of the fluid. So in some cases we need the high pressure fluid. So in that cases we use compressor. We give some work input in it, and it helps to increase the pressure of the liquid. And it is used in a gas turbine power plant and a vapor compression refrigeration system. And in this case, pressure at output is greater than pressure at input, whereas in turbine, pressure at input is greater than pressure at output. So the steady flow energy equation in this case will be rate of heat interaction is equal to control volume work rate plus kinetic energy rate of change of kinetic energy rate plus change of potential energy rate plus change of enthalpy energy rate. And this is for the compressor. Now, when we talk about the well insulated compressor, in this case, when we talk about the well insulated compressor, our general equation becomes omega CV, the rate of control volume work plus the rate of enthalpy change will be equal to 0. since in this case, firstly though we know that there will be no heat interaction since it will be zero, and kinetic energy change and potential energy change rate are very small, almost very small. So that's why we ignore it, and this is the case for the insulated system. And also for turbine, in case of turbine, so we actually like haven't brought it over here. When the turbine is insulated, we similarly write this same formula in case of turbine as well, since kinetic energy and potential energy are almost zero and heat interaction is almost equal to zero. In case of insulated turbine and compressor, this is the formula. Formulas are quite same. We need to remember this pressure difference. So what we have done is we started from the steady flow energy equation, which is the general form, which came from energy flow equation. In the energy flow equation, there is a term called delta E as well, but in this case we know there's mass flow rate, and the energy with respect to time will be zero almost in case of steady flow. That's why we haven't wrote that. So in a steady flow energy equation system, our equation is the rate of heat interaction is equal to the rate of work, control volume work, plus kinetic energy change plus potential energy change rate plus enthalpy energy change rate. And when we divide it by the mass flow rate, which is m dot, then there's the kinetic energy rate will become half c naught square minus ci square, and potential energy rate become m dot n naught and g z naught minus zi, and delta hi become h naught minus hi. And this is the case of the nozzle. The first case we have studied was nozzle. Nozzle helps to as I have said already, nozzle is a steady flow device. It helps to increase the kinetic energy and it is used in jet propulsion as well, and in impulse turbine as well, at the inlet of impulse turbine. And we see that speed at output is quite higher than that of speed at inlet. And similarly, we have talked about diffuser as well. And by the way, this heat energy transfer equation for this is this. Since the work energy, control volume work is not there in this case, that's why it's like this. And we need to remember the unit, watt and kilowatt. And in an insulated case, there's a heat transfer 0, and potential energy transfer is also 0 in horizontal insulated case. Similarly, in diffuser, our formula is same. Whereas in case of this nozzle, it helps to increase the kinetic energy, but in case of diffuser, it helps to increase the pressure in the system. Our system is right now diffuser itself, so it helps to increase the pressure, and pressure at output is greater than that of pressure at input. Similarly, when nozzle is diffuser is insulated, the rate of kinetic energy change plus horizontal in a horizontal place, rate of kinetic energy plus enthalpy change will be equal to 0, since rate of heat transfer interaction is equal to 0, and potential energy interaction is also 0 due to height, quite same in this case. So now turbine became, and we know that in turbine there is a work output, and pressure is when the turbine is rotated with the pressure Pi or power Pi, and there will be output Po. Pressure at output is less than that of pressure at input, since it helps to rotate the turbine, and after that pressure at output is go through that output valve. So at pressure at input is greater than pressure at output in case of a turbine. And the energy equation is quite similar to that of an SFEE general equation, and its unit is watt per kg, since control volume work is in here. So when it's divided by the mass rate, flow rate, it becomes the equation, and its unit is joule per kg. Kelvin. And compressor, when we talk about it, compressor is quite that structure is quite similar to the turbine, but in an inverse way. First, we give some work to the compressor, and it helps to increase the uh, pressure of the liquid. So pressure of output is greater than pressure of input in this case, and it's also have the same formula. And in both cases of turbine and this compressor, both have when insulated and placed in a horizontal direction, their formula is rate control volume flow plus enthalpy rate of change of rate of enthalpy rate change will be equal to 0, since convection energy and kinetic energy is almost 0 and heat transfer is 0. So if you understood this video, please subscribe my channel, and if you have any doubt, you can comment. Thank you for watching this video and have a nice day ahead.